We're going to continue our work on functions by talking about piecewise defined functions. So up to now, we've looked at functions that we've only represented by one function rule. This is exactly what was done with the function, and then we worry about the domain. We've never had a function that behaved differently over different pieces of its domain. But in real life, functions are represented many times by a combination of equations that correspond to different parts of the domain. And those functions are called piecewise defined functions. So here we have a function that has pieces. We can see from the graph its behavior for all domain values less than or equal to +1 is it acts like the parent function y equals x squared. But for all values greater than 1, it acts like the linear function 2x plus 1. So we don't have any worry about failing the vertical line test. Everywhere that I draw a vertical line here, we don't have any overlapping outputs based on our input values. This is indeed a function. If this was a closed-in hole right here on this piece, then we would fail the vertical line test. That's why that's an open hole. So for all input values less than and equal to 1, it behaves this way. For all input values greater than 1, it behaves this way. So this is a piecewise defined function. It's defined in pieces. So let's consider this function. Here's another one. And this is what the function rules usually look like for piecewise defined functions. We have, and it's kind of hard to see here, but we have different pieces of what is being done to domain values. Here, domain values are given, and then we just add 2, and that gives us our y values. Here, we take the domain values and square them. So we have different behavior for different pieces of the domain. So here's what a function rule looks like for a piecewise defined function. For all values between 0 and 2, not including 0, but including 2, it acts like a line of slope 1 that has a y-intercept of +2. For all values greater than 2, it acts like the parent quadratic function. So let's look at a table of values and see how we might fill that table out. So here are our x and y values. When x is -1, now for a piecewise defined function, I have to worry about which piece of the domain I'm going to plug that x value into. -1 is not included in this piece, so I can't plug it in there. I need to plug it into this piece. So f of -1 is going to look like -1 plus 2. So that would be an output of 1. F of 0 is also in this piece of the domain. So I'm going to use that part of the piecewise defined functions rule, and we'll get an output value of 2. F of 1 is also in that piece. So I'm still going to plug in f of 1. I'll get an output of 3. F of 2, now I need to pay attention because this is where the behavior of the function changes. F of 2, when x equals 2, is still included in that linear piece of this piecewise defined function. So our output there would be 4. But now I am at a domain value that is in this part of the domain. So now when I find f of 3, I have to pick up this operation because this is defining what's happening there. So the output here is 9. And when f is 4 as well, I'm still in this part of the domain. So f of 4 is going to look like 4 squared, or 16. So when we're looking at a piecewise defined function, this is important information. It's as important as the definition of the function rule. So let's look at this function and let's try to sketch it. We just had this one, we found a table of values. Let's draw the plane as nearly as we can here. I know how these functions look in the plane. Here's x equal 1 and x equal 2. My function changes over 1 and 2. So let's just put some tick marks here, or my function changes over x equal 2, I should say. This function is undefined for any value less than 0. So let's say I was going to draw this whole line. This is a line of slope 1, right? And it has a y-intercept of x equal 2. But I can't draw anything less than 0, and 0 is not included in here. This line goes up to and includes 2. Everything after that, every x value greater than 2 that has to do with this line is not going to be included in this drawing, in this graph. So there is the piece of the line x plus 2 from 0 up to and including positive 2. Now let's get another color and let's draw that function. This function behaves like this, right? It is a parabola that opens up, but I'm only interested in the values from here to positive infinity. So every other part of this, I'm not interested in. I'm not interested in any of that right there. I'm only interested in the part that is greater than 2, and it doesn't include 2, so that has to be an open hole. So there's the graph of this function. Not very difficult to do, but this plays a key role in how your function behaves over what interval of the domain. So not difficult to draw these graphs, but you just have to pay attention. So here's another piecewise defined function. And our function can have many, many pieces. It doesn't just have to be 2 pieces. It can have a lot of pieces. Here, this function behaves like the line x plus 3. It has a positive slope of 1. It has a y-intercept of 3. It behaves this way from negative 2 to 1, including negative 2, but not including 1. Then it behaves like the horizontal line y equals 3, only at x equal 1, just at that one point. So this function contains the point 1, 3. And it behaves like a negatively sloped line, a slope of negative 1, translated, or having a y-intercept of positive 3 for all values greater than 1 in the plane. So let's do A. Find f of negative 1. Negative 1 is in this interval, so I'm going to use this piece of the piecewise defined function. So that is negative 1 plus 3, or 2. F of positive 1 is not in this interval. It's right here. So f of 1 has to be 3. F of 3 is in this interval of the domain. So that is negative 3 plus 3. So that is going to be, sorry, my technology's freaking out for some reason. Clearly that's going to be 0. So whenever it gets through freaking out, we'll continue on. So not sure what happened. I think I got it fixed. We'll continue on here. So we were finding f of 3, and we said that that is going to be part of this domain. So that is negative 3 plus 3, which is 0. So find the domain. Well, here are the pieces of our domain. We know that we are going to start at negative 2. There's no other domain value on here smaller than negative 2. And we're going to go up to but not include 1, but this includes 1. So 1 is included in the domain. Also, all values greater than 1 are included in the domain. So this is actually what the domain of this piecewise defined function would look like. So we just need to look at the different pieces and see what is included and what is not included in those pieces. So now let's talk about graphing this function. I'll see if I can graph it fairly quickly. The linear behavior is going to help us here. So the interesting values that we're looking at are -2 and 1. That's pretty much where the behavior changes. So from -2 up to including 1, it is this positively sloped line with a y-intercept of +3. So it's going to have a slope of 1. So there would be -1. So there's what a slope of 1 would look like, right? So now I'm just going to give it a slope of 1 as near as I can, and it's going to behave that way from -2, not including any values less than -2. I will get this technology figured out before too long. I have an open hole here on this piece because it's not included. And then we have an output of 3 at x equal 1. Well, here's x equal 3. So that takes care of this piece. Now this piece is a negatively sloped line with a y-intercept of +3. So it comes down through here and would start, I don't know, somewhere along here, and it's going to continue to go to positive infinity. So there are the three pieces of our piecewise defined function, and that's what the graph would look like. It would have this linear piece, it would have this one point, and it would have this other linear piece, and we would have to show that it continues to go to positive infinity as far as our domain values are concerned. So not difficult to draw a piecewise defined function. Now in our last lesson we talked about our parent function of the absolute value function, and I showed you that it is indeed a piecewise defined function. So we could definitely deal with the fact that now we're dealing with a piecewise defined function here. So let's talk about word problems, because piecewise defined functions do model what's happening in the real world quite nicely. So your favorite dog groomer charges according to your dog's weight. If your dog's 15 pounds and under, the groomer charges $35. If your dog is between 15 and 40 pounds, she charges $40. If your dog's over 40 pounds, she charges $40 plus an additional $2 for each pound. So clearly, just from the words very quickly, we can see that our domain, the price that she charges for grooming, is broken up over these values: 0 to 15, 15 to 40, and over 40. Now, the behavior of how that gets handled is based on what's happening here. All dogs from 0 to 15 pounds, it's a standard flat rate of $35. All dogs from 15 to 40 pounds, a standard flat rate of $40. But if they're over 40 pounds, then she charges $2 additional for each pound over 40. So this is what the piecewise defined function would look like for the word problem that we have here. This is actually what the graph would look like. So the graph is piecewise. It's a horizontal 35, horizontal 40, and then a line with a slope. So this says, what would the groomer charge if your cute dog weighs 60 pounds? Well, if your dog weighed 60 pounds, we're in this part of the domain, x greater than 40. So she's going to charge us 2x minus 40, and that would be $80. So pretty straightforward. We'll work with some piecewise defined functions when you come to class next time, and you'll be more comfortable with them.